Hi guys, welcome to section B, chapter 11. Kind of a tricky lesson today, so buckle up and get ready, okay? We're going to keep talking about movement, and now we're going to talk about how quickly things are moving. We could talk about the speed of an object, which is a very common way to talk about things. That is a scalar measurement. Remember, it's just a number, it has nothing to do with direction. So, I can drive my car home at 45 miles per hour. That's its speed. And what I'm actually doing is I'm figuring out how much distance I traveled in a certain amount of time. So it's distance divided by time. That's this formula right here, okay? But a lot of times the speed isn't enough. I need to know the direction that the object is going. And so once I add the direction to that amount, it becomes a vector measurement. And it has a different formula, okay? Remember that delta means change. So if I have delta x, that's our change in our displacement, change in our position over a change in time. That's the formula for velocity. And remember, the book uses those bold letters to show vector quantities, okay? So let's calculate some speed. This formula down here in the bottom is the formula we're using. We're looking for speed. Now, the reason it's written in a triangle, the way this formula works is you can rearrange it and manipulate it. And this little triangle template allows you to know how to calculate the missing piece, okay? If I'm trying to solve for speed, that means I'm actually dividing distance by time, because that's what's in the triangle, okay? If I'm missing time, that means I divide distance by speed, because that's my other two quantities there. If I've got speed and time, but I'm looking for distance, I multiply those together, okay? So that's how that triangle works, okay? For the most part, we're just going to be using the speed equals distance divided by time formula, okay? So let's look at this example. Imagine you're on vacation and you traveled 1,232 kilometers, and it took you 14 hours to do that. What is your speed, okay? Now, in real life, you probably aren't going the exact same speed all the time, but for these calculations, we're just going to go ahead and assume that it is. It'll kind of give you your average speed, okay? So our distance is the 1,232 kilometers, and our time is the 14 hours, and we divide those two things, okay? Now, distance for this example is in kilometers. Time was in hours. And so whatever those numbers divided are, there's our number, but we also have to pay attention to the label. It's always going to be a distance per time, and you want to use the same units that were given to you in the problem. So this is 88 kilometers per hour, okay? Velocity can also be calculated, okay? Remember that delta x is our change in our position, and then the delta t is the change in time. So I've got a horse, and it moves from 10 meters east of the gate to 45 meters east of the gate, and it takes 15 seconds to do that. What is the horse's velocity, okay? So we take the final position, subtract the initial position from it, so 45 meters east minus 10 meters, that's a difference of 35 meters, okay? So that's right there. And then the time was 15 seconds, okay? So 15 divided by 35 divided by 15 gives us 2.3. We've got our meters per second, but since we're talking about velocity now, I need to make sure and include the direction. So the proper answer is 2.3 meters per second east, okay? Now we can add these velocities, and if the object is moving in the same direction, it's a lot easier to deal with, okay? Because both quantities would be considered positive. If I don't know, I threw a ball and it was going 10 meters per second, and then it slowed down and it was only going 8 meters per second, but they were still traveling west in the same direction, and so on and so on, okay? I could just add that up and take the distance into account to come up with the velocity, okay? The example in the book says if I have a plane that's traveling west, a 720 kilometer per hour plane traveling west, and then a wind of 83 kilometers per hour west, they're both moving in the same direction, so you're going to add them together to come up with the total quantity. I wrote the wrong answer there. This is 803 kilometers per hour. I missed a 3. That's kind of a big deal because I just add that 720 to the 83, okay? But sometimes things are moving the opposite direction. So if I have a plane moving this way at 100 kilometers per hour, and the wind is going in the opposite direction at 25 kilometers per hour, I make one of these quantities positive and the other one negative. And it doesn't matter which is which, okay? It's just because they're in opposite directions. So then I really am finding the difference between those things. So the velocity of that plane would then be 75 kilometers per hour because the wind is countering it a little bit, okay? There's another example in your book. It talked about a 720 kilometer per hour plane traveling west, and it's flying into a wind that's traveling east, okay? So an 83 kilometer per hour wind traveling east. It was given that negative because it's in the opposite direction. And so the difference between those two would give us the overall velocity of that plane of 637 kilometers per hour, okay? Now we've got graphs that can kind of demonstrate some of the different types of motion as well. When I have a nice, straight, consistent line like that, that tells me that the velocity is constant, okay? It's going at a steady pace. And you can see that my time is down here and my distance is here. So those two amounts are still being compared by this, okay? My advanced math people, you guys know how to calculate the slope of a line, okay? I've got the rise over run. And so if I calculate the slope of that straight line right there, that's actually going to give me the speed, okay? But what about this curved line? I've got this funky one going up. It's not a straight line. That curved line tells you that the object is actually accelerating. As it's going, it's starting to go faster and faster and faster. We'll talk about acceleration in the next section, okay? Now look at this portion of the line, this horizontal portion, okay? Time is still going on, but if I take this line out to my y-axis, I see that distance isn't changing. So what that tells me, when I see a horizontal line like that, that means that the object is not moving anymore. Time is still going forward, but the object is not moving, okay? So that's just some different ways that we can show different types of movement on a graph, okay? All right, let's talk about momentum. Momentum is represented with lowercase p. It's bold, which means it's a vector quantity. And it's basically just mass times velocity, okay? And the easiest way to think about this is with objects of different sizes, okay? If you've got a really big, high school senior football player and a little tiny kindergartner, okay, and they're running at the same speed towards each other, which one's going to have more momentum, okay? If their velocity is the same, their velocity should kind of cancel each other out. But we all know that big, huge football player is just going to bowl right over that kindergartner. Because the higher the mass, the higher the momentum, okay? So if I increase the mass, I increase the momentum, okay? But what about a little tiny bullets? They're really, really small and they cause all kinds of damage, okay? The mass of a bullet is really small, but it travels at an incredibly high velocity, okay? And so that also increases the momentum. You can either increase the mass to increase momentum or increase the velocity, okay? A car rolling isn't going to do very much damage, okay? It's going to have enough momentum to probably knock you over, but not really do a lot of damage. If I add the mass of that car with a high velocity of the car, you can't stop it. There's too much momentum to stop, okay? Our label for momentum is, we've got the mass label there, and then we've got that velocity label there. So kilograms per meters per second is one version, but basically it's whatever you measured the mass in and whatever you measured your distance and time in for the velocity, and you're going to have to use all three of those, okay? Now there's this thing known as conservation of momentum. In a closed system, the momentum stays totally the same, and I can demonstrate this with this fun little toy right here, okay? So whatever this mass is, okay, I'm gonna swing it down. and it's going to slam into this other stationary ball right here, okay? But its momentum is going to be conserved, and you can see it like this, okay? So the momentum actually travels through these middle stationary balls, and it allows this one to move, okay? Now watch what happens when I do that with two of these, okay? Okay, because the mass of 2 is not the same as mass of 1, so it's not going to send just one of these over. It's going to actually have to send the same amount. Okay? Watch what happens when I send 3 over. Make a guess. You see? Keep swinging 3 like that. All right? We'll play with this in class a little bit more. I love this toy. All right. Calculating momentum, okay? Momentum is the mass times velocity, all right? So this is just kind of a little mind game here. How could a 1 kilogram rock, which is about the size of a baseball, have the same momentum as a little tiny 1 gram bullet, okay? Increasing either the mass or the velocity will increase the momentum. I just talked about that on the last slide. Since the rock has a higher mass, it's going to have a lower velocity. I can only throw a rock a certain velocity, okay? The bullet, this should say lower, has a lower, I must have been in a hurry when I made this one, excuse me, has a lower mass, but it has a much higher velocity, okay? So 1 kilogram rock, let's say I can throw it at 1 meter per second. If I have a 1 gram, I have to use the same labels here. So I've converted that 1 gram into 1,000th of a kilogram. That's the same thing. But it's moving at 1,000 meters per second. These things are actually equal to each other. If I multiply 0.001 times 1,000, it gives me 1. It gives me 1 kilogram per meter per second. 1 kilogram times 1 meter per second is 1 kilogram per meter per second, okay? So I had, if the mass is really low, the velocity goes up. If the mass is really high, the velocity goes down to equal those things out. Okay. That was a tough one. See you guys.